Morning, Chichi.
Good morning, sir.
How are you today?
I'm okay, sir. Thank you. How are you?
I'm better. Can't complain
Okay.
really. Yeah. Apologies, man. Look, I'm out of office. I'm working from home the whole week. So I made a mistake of forgetting my charger in the office. And I've ordered one. It took so long to arrive. I only got it yesterday in the afternoon. So it's only now that I'm able to communicate with you guys.
Oh, it's
Uh,
okay, sir. Thank
all right. No, you're welcome. You're welcome. Yeah. I don't know if others will be joining us, and it's almost 9:45 now. Let's give them some few minutes and check if they are joining, but stay on the line. If they are not joining, then we shall proceed. They will find us already working. I think I gave you a task to do the remaining 3 questions of chemical equilibrium, isn't it?
Yes, sir.
Okay. Yeah, so we'll start off by doing that, and then so that next week, I promised you guys that we're supposed this week to start with work, energy, and power. Yeah, this week next week actually, we're gonna be doing work, energy, and power. Which questions were those? Can you remind me again? The remaining questions. Was it 14, 15, and 16?
It was,
Yeah, I think it was 14 to 16, né?
yes, sir.
All right. Not sure if others will be joining in, but we better get started. They will find us. If they are joining, they will find us working already. All right, can you see what's on my screen?
No, sir, I can't.
But I'm already sharing the screen. Still can't see.
I can't, sir.
Then something is wrong with your connectivity. I'm already sharing the screen.
And now,
I'm stopping, sharing again. You still can't see anything.
I can see it now.
Okay. All right, then let's get started. Sit comfortably. Hey, come on, man. All right. Let me check if others are joining in. Okay, it's still just a 2 of. Okay, I don't see any reason why we should not proceed, because I have already sent out the message to invite everyone. So let us move on to doing this question 14. So unfortunately, due to not having my charger, I could not check your work. Okay, so yeah, I promise you to upload the recorded lessons. I'm definitely gonna be doing that as soon as I get back to the office on Monday after our lesson. So you'll get all the recordings that I'm able to access. So I'll try
Thank
to
you, sir.
share them in the order from momentum to the rate of reactions up to where we are at now. So I will upload those. Now let's look at this. The balance equation, the The equation below represents the reaction used in the Haber process to produce ammonia. Very well-known process, excuse me, useful in the production of fertilizers, industrial production of fertilizers. It's one of the first steps there. So there you have the balance equation, and they are also telling you that this is an exothermic reaction. Indirectly so. In industry, the product is removed as quickly as it is formed. Why is it removed? Because when we removed the product, then we're going to produce more of the product. When you remove more the ammonia, more of ammonia will be produced. Because that is in alignment with the Lechi-Tillers principle. When you remove either the reactant or the product, more of what you are removing is going to be formed. The equilibrium position will shift towards the side where there is a shortage. The equilibrium position shifts towards where there is a shortage and away from where there is excess. So when you add something, the equilibrium position shifts away from where you have added. When you remove something, equilibrium position shifts towards what has been removed. So in this case, by quickly removing the ammonia, we are making sure that more of the reactants will react to produce more ammonia. I don't know if that makes sense.
Yes, sir.
So want to get more of ammonia. And by removing the ammonia as it is formed, we are making sure that the equilibrium position is always shifting towards the side of the product, meaning we always want to favor the forward reaction. Okay. My phone is ringing and I can't find it. All right, as we forge forward. So first question, you know the meaning of the double-headed arrow, right? The double arrow. What is the meaning of the double arrow there, Chichi?
A reversible reaction.
Indeed, that is so. The reaction is reversible. So it must be taking place in a closed container also. Give one reason why it's removed from the reaction vessel as quickly as it formed. We have already discussed that. So that we can produce more of the ammonia. To produce more of ammonia. That is why we are removing it. Because the intention is not for the reactor, for ammonia to react and form the reactants, but to get more ammonia. Okay? To produce more ammonia. And we can use the Lechi-Tillers principle to explain why. Removing the product would mean now we've got more of the reactants. Hence, the reactants will react more frequently to produce more of the ammonia. Let us look at that. The graph below shows the percentage yield of ammonia at different temperatures. At different temperatures, as you can see, we have already mentioned that the reaction is exothermic. Look at your production at 350 degrees Celsius. You are producing about 45, the maximum. At 450 degrees Celsius, the production drops as the reaction proceeds. Oh, it's the pressure, sorry. It's the pressure at different temperatures. So let us look at what happens when we increase the pressure. As the pressure increases, we are forming less and less of ammonia. Is it in alignment with what we are expecting? Remember, when we increase the pressure, we are going to favor the side with fewer molecules. Now we look at this. For this to make sense, I think we need to look at just one temperature. Look at your 350 degrees Celsius. When the temperature is kept constant and the temperature and the pressure is increased, look at what happens. This is your pressure, by the way. Do not think this is a temperature axis. It's a pressure axis. So as the pressure increases, the production of ammonia also increases at a fixed temperature. Currently we're looking at 350 degrees Celsius. The same is true, but when we increase the temperature, we notice the same trend. But now, due to the increase in temperature, the production is getting lesser. Yes, it does increase with an increase in pressure, but at higher temperature, we are getting lesser ammonia than at lower temperature. I don't know if that makes sense.
Yes, sir, it does.
So that is a trend that we're observing. So if you look at each individual temperature, starting from 350, you notice that the graph is an increasing graph, which means as the pressure increases, the production of ammonia also increases. But once we increase the temperature at the same pressure, let's say at the same pressure of 100, and we increase the temperature now from 350 to 450, the production drops drastically. Why is that the case? Because the forward reaction, which is a production of ammonia, is exothermic. It can only be favored by decreasing the temperature, not increasing the temperature. Right, let's move forward. Any questions before we look at this?
No, sir.
No questions. Right, let's clean up this graph so that we can easily read. Let's clean up. So you are going to read each of these curves individually against the pressure. Do not try to compare them simultaneously because it's going to confuse you and you're going to misinterpret them. So look at this graph at a given temperature and look at the trend. What happens to the percentage yield when the pressure increases? And you will see the trend at a fixed temperature. Write down the percentage yield of ammonia at a temperature of 450 degrees Celsius and a pressure of 200 atmosphere. So there is the curve that they want us to look at a pressure of 200. That is very obvious, isn't it? That is very obvious. It's 20%. That is a percentage yield, 20%. 14,4. Refer to Leschetizer's principle to explain each of the following deductions made from the graph. For the given pressure, the yield of ammonia at 500 degrees Celsius is much lower than at 350 degrees Celsius. Okay? For a given pressure, take for example, that 200. At a pressure of 200, the percentage yield at 500 is less than 10%. And then at 350 is just below 40%. It could be maybe 38% to give it a rough estimate. That is what they are saying. So now they are saying, let us use the Leschetizer's principle to explain those deductions made from the graph. So how can we explain? We are looking at the effect of temperature. The effect of temperature at a fixed pressure. So why is this the case? So we tell them firstly that the forward reaction is exothermic. First and foremost, forward reaction is exothermic. The reason for that is because the heat of a reaction is negative. That's the first thing that we need to flag out. Tell them that their forward reaction is exothermic. The production in this case, this percentage yield that you are referring to of ammonia can be increased by lowering the temperature at a fixed pressure or at a given pressure. It is for that reason that at 350 degrees Celsius, we have the most than at 500 degrees Celsius. It's because the forward reaction is exothermic. So increasing the temperature from 350 to 500 favors the reverse reaction. Will favor the reverse reaction. Hence, we get less ammonia at a higher temperature because the production of ammonia is exothermic, not endothermic. So we need to lower the temperature. I don't know if there's any question before we move forward. Any questions? Chinonya is still there?
Yes, sir. No question, sir.
All right. Okay, let me check if. Oh, they Sidwell. Sidwell, good morning. Are you well, Sidwell?
Yes, sir.
Okay, my volume is a bit low. Let me increase it. Okay. That's great. That's great, Sidwell. Let's proceed. I hope you didn't miss much of what we are looking at. We are looking at question 14, basically, Sidwell, which is part of the homework that I've given you last week. I couldn't be reached there for the rest of the week from Monday until to yesterday because I'm working from home and I forgot my charger, my laptop charger in the office. So I had to order a new charger. It only arrived yesterday in the afternoon. So it's only today that you're able to have a lesson. So please forgive me for that. For a given temperature, the yield of ammonia at 350 atmosphere, that is pressure, is higher than at 150 atmosphere. Why is that the case? Why is that the case? Remember, what are we doing here? We are decreasing the pressure from 350. 350 is here, 150 is there. For a given temperature, we can take any of the temperatures, whether this 500 or 450 or the other one. It matters not. But we are looking at different pressures. 150 is here. Let's look at this one. Look at this. At 150 against 350. So as the pressure increases, the percentage yield of ammonia also increases, which means as we increase the pressure, we are favoring the forward reaction. Remember, what is the effect of increasing in pressure? Increasing the pressure will favor the site with lesser moles of the gas. In your reactant, we've got 4 volumes of gas. In your product, we've got 2 volumes of gas. So obviously, by increasing the pressure, we are going to favor the forward reaction, which is the production of ammonia. The production of ammonia. So the reason why at a higher pressure, we have higher percentage yield of ammonia is that because when we increase the pressure, the forward reaction will be favored. Okay, so let us explain that to them, that increasing pressure, increasing the pressure at a fixed temperature. Remember, we must keep the temperature constant while we are doing that. Will favor the side with fewer gaseous or gas molecules. So this is what will happen. We already know this. This is a fact that we are stating. It's a fact that we are first stating. What is the effect of pressure? We are stipulating that. Then now we go and interpret the balanced equation. Then we tell them that the forward reaction in this case has fewer gas molecules than the reverse. So if that is the case, then we can tell them then, hence, increasing pressure favors the side with fewer gas molecule, which is the forward reaction. It is for that reason that we see that trend that at a given temperature means look at one graph, maybe at 450 degrees Celsius, like we have done that. So we see the trend that this is an increasing curve. This curve shows an increase with an increase in pressure. The increase in the percentage yield as the pressure increases, that is a trend. It's a trend that you are observing there. For all these curves, as you can see them, they are increasing as the pressure increases, whether it's 350, 450, or 500 degrees Celsius. But you must look at one curve at a time. In this case, we are looking at the curve in the middle, which was obtained at 450 degrees Celsius. 450 degrees Celsius. We see that as the pressure increases, the production of ammonia or the percentage yield of ammonia is also increasing. And the reason for that is because in the forward reaction, there are fewer gas molecules compared to the reverse reaction. Hence, the increase in pressure favors the side with fewer gas molecules, and that is the forward reaction, which is a production of ammonia. Any questions before we move to the next? Right, let's hear this one. A technician prepares ammonia by reacting 6 moles of hydrogen and 6 moles of nitrogen. In this case, you need to know which one is the limiting and the limiting reagent, limiting and the excess reagent, between hydrogen and nitrogen, in order to get the maximum number of moles. How do I get that? We can get that by comparing the theoretical ratio, the stoichiometric ratio from the balanced chemical equation. 14,5,1. Remember that you are looking at this balanced equation. This is what you are looking at. And what do we notice that? We notice that the theoretical ratio at which nitrogen gas should be mixed with the hydrogen gas is 1:3. The 1:3 comes from the balanced equation. So what would happen if I multiply this whole thing by 6? Then I will get that 6 moles of nitrogen gas requires 18. 6 times 3 is 18. So if I multiply this theoretical ratio from the balance equation by 6, I'm obtaining that 6 requires 6. This is the theoretical ratio, both of this. Theoretical ratio. But what is the actual ratio? This is what stoichiometry is about, by the way, guys. Stoichiometry is about comparing the theoretical ratio to the actual ratio. But what do I actually have? According to the statement above, they said 6 moles of hydrogen gas only react with the 6 moles of nitrogen gas. So the actual ratio, let me use a different color this time. So what is actually happening here? And this will help you to easily identify your limiting reagent. The actual ratio now says the nitrogen gas is reacting with the hydrogen gas at a ratio of 6:6. Look at what we have. I needed 18 moles to react with 6, but I only have got 6 moles reacting with 6. So there is a shortage of hydrogen gas. There is a shortage of hydrogen gas because 6 moles, according to the balance equation, the ratio 1:3 is equivalent to 6:18. Oh my goodness. My eye is itching badly. So guys, I hope you are listening to this. I don't know if that makes sense to you guys. Can you still see what is on my screen?
Yes, sir.
Okay, so I'm saying to you, from the balanced equation, this comes from the balanced equation, by the way. The 1:3 is from the balance. It's a stoichiometric coefficient from the balance equation. We just took that directly. Then we multiply that ratio 1:3 by 6 to obtain 6:18. So theoretically, we must mix 6 moles of nitrogen gas with 18 moles of hydrogen gas. But what do we actually have? We only have got 6 moles of nitrogen gas reacting with only 6 moles of hydrogen gas. There is a shortage of the hydrogen gas to react with the nitrogen gas. According to the required theoretical ratio. Because there is a shortage, if there is a shortage of hydrogen gas, then that which is in shortage is a limiting reagent. A limiting reagent is what will determine the maximum production. The limiting reagent is what determines the maximum production. Therefore, to look at the maximum production, I need to take the limiting reagent and compare it to what I need to produce. From where? Starting with the balance equation. From the balance equation, 3 moles, okay, sorry. Why this thing over? 3 moles of hydrogen gas will produce 2 moles of this. Theoretically, I've got 3 moles of this producing 2 moles of that. And what is this? Is from the balance equation again. It's theoretical ratio. But what did I actually mix? According to the statement, 6 moles of this will produce X moles of that. I don't know how much I'm going to produce. And then to get that, by now, I think we all know 3x is equals to 2 times 6, 3 times x, 6 times 2. Then we divide both sides by 3 to get that x is equals to 4 moles. That is the maximum production of ammonia gas. As you can see, this is a simple mathematics of grade 6. No, I'm lying. Grade 8, not grade 6. Grade 8. Ratios and proportions. Any questions? So the maximum production of this that you are going to get is 4 moles of ammonia. That is the maximum production. To do that, we needed to find the limiting reagent first. We wouldn't achieve that. If we need the maximum production, first thing first is to get the limiting reagent. You get the limiting reagent by comparing the theoretical ratio to the actual ratio. But theoretical ratio is from the balanced equation. Then actual ratio is from the given statement. This comes from the given statement that we have mixed 6 moles of nitrogen gas with 6 moles of hydrogen gas. Any questions so far? Any questions so far? Sidwell? Chinonye, any questions?
No,
No
sir.
questions.
All right, let's wrap this up then with 14,5,2. I think I'm gonna need a clean page for this one. The above reaction now takes place in a 500 cubic centimeter container at a temperature of 350 degrees Celsius and a pressure of 150 atmosphere. So we go there, we look at the percentage yield, very important. What is the percentage yield of the ammonia gas at a temperature of 350 and a pressure of 150? We look at this. There is 150. There is 350. The percentage yield is 35%. So at the given temperature and pressure, the percentage yield of this ammonia is 35%. The system is allowed to reach equilibrium. Use the graph above to calculate the Kc constant for this reaction under these conditions. So how do we go about doing that? Let's look at that. 14.5.2. We look first at the percentage yield of ammonia at the given temperature. We have found that it is 35%. So 35% of what? It is 35% of the maximum production. The maximum production, the 100% production is 4 moles. And what is 35% of that? Is it 1,4?
Yes, sir.
It's 1.4, right? So we know exactly now that at the temperature of 350 degrees Celsius and the pressure of 150 degrees Celsius, the maximum production, let us treat that correctly, 150 atmosphere and 350 degrees Celsius. Yes, that is exactly. So this is 350, the curve at 350 degrees Celsius, pressure of 150 atmosphere. The maximum production there is 35%. But 35% of what? Of the maximum production. What is the maximum production? It's 4 moles. So when the equilibrium is reached under those conditions, we'll have produced 1,4 moles of ammonia at equilibrium. And only now can we be able to design that table. So I hope you guys are following here. And if you ever get lost, please do not be afraid to stop me so that we are all working together here. No one must be left behind. So we've got the nitrogen gas reacting with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. Then we look at your initial moles. Then we look at the change in moles, which is your reactant moles. And then we look at our equilibrium moles. Initially, we are told we mixed 6 and 6, there was none of that. At equilibrium, we have just calculated, or we just established that we have produced 1,4 moles of the ammonia gas. So this is what we have to start our table with. Because remember, at the beginning of 14,5, a technician prepares ammonia by reacting 6 moles of hydrogen gas and 6 moles of nitrogen gas. That is where we are starting, 6 and 6. And then we just calculated the equilibrium moles of the ammonia and found out that it is 1,4. Remember now that the change in moles will be in terms of your of X. So according to the balance equation, 1 mole of that will react. The reactants are decreased to produce the product are formed. So it's a plus 2 moles of that. And remember that this will be just equals to 2x. This will be 6 minus 3x. This will be 6 minus x. So what is the value of x so that we can get the equilibrium moles? We can get the value of x from here because we are combining these two to get that. We combine this to get this. We combined that to get that. So we've combined all of this to get to this point, to get to this point. So now, in order for us to get the value of x, we are going to equate that to this. In order to get that, this is actually 0.7. Then we can back substitute to get the equilibrium moles. Which is what we need of nitrogen gas. For our nitrogen gas, it's 6 minus x. 6 minus 0.7, and that is 5.3 moles. And then we can also find the equilibrium moles of your hydrogen gas, which in this case is 6 minus 3 into 0.7. 6 minus 2.1, that is 3.9. Am I correct?
Yes, sir.
3.9 moles. Thank you for that. Now, once we have that, we can now calculate our equilibrium concentration, starting with your ammonia. We have 1.4. Remember, the volume is 500. If volume must be cubic centimeters, not decimeters. So remember to convert before that. Let's write the formula first. C is equals to N over V. Let's shift you so that we can write the formula nicely. So when we divide here, we get 2.8 moles per cubic decimeter. Then we can get your moles of hydrogen gas. For our hydrogen gas, we got 3.9 divided by 0.5, and that is 7.8 moles per cubic decimeter. Last but not least, the moles of nitrogen gas at equilibrium would be 5.3 divided by 0.5, and that is, I think, 10.6. No, I don't think it is 10.6 moles per cubic decimeter. And there we've got our things. Then the next thing, we can now work out the Kc expression. Nitrogen gas from the balance equation, stoichiometric coefficient is 2. Hydrogen gas from the balance equation, stoichiometric coefficient is 3. Nitrogen gas, stoichiometric coefficient is 1. Then we substitute 2.8 to the power of 2. Hydrogen gas, 7.8 to the power of 3. Lastly, 10.6. I don't know what the answer will be, but it's a very small number. What is the answer?
1.56 times 10 to the power of negative 3.
Negative 3.
Yes, sir.
Thank you. So Kc has got no SI units, remember that. So that is basically what you were supposed to do. The tricky part was to note the percentage yield at equilibrium and not use the maximum production. Remember, this that we have calculated here is the maximum production. If all the reactants were used up, you would get 4 moles of ammonia gas. But because this is a reversible reaction, no, you can't use up all the reactants because the product will also react to form the reactants. And the reactants are simultaneously reacting to form the product. It's a reversible reaction. Therefore, you can't reach these 4 moles in a closed container. This will be, if this was taking place in an open container and we're collecting all the ammonia gas that we're producing, we're going to get a maximum of 4 moles. However, under the given conditions, at a temperature of 350 degrees Celsius and a pressure of 150 atmosphere, we only have got a production of 35% of the maximum production. We only have 35% of what is maximum. We only have 35%. That was the catch. You didn't produce 100%, which is 4 moles of this. You only have 35% of those 4 moles, which is what we started with. This is 1,4 moles of ammonia gas when the equilibrium is reached at 350 degrees Celsius and a pressure of 150 atmosphere ATM. That was the catch. That was the only catch on this. Understanding the concept of percentage yield. Any questions from your side? Chinonya and Sidwell. Any comments?
No, sir.
That means we can move on to question 15, I suppose. Sidwell. Okay. I don't understand why this is like that. Okay. But you're going to have to split it into 2 because it doesn't want to show everything. Right. Question 15, we'll cut it into 2. So for the question 15, this is what we have. Right, initially, I hope you are listening, 60,8 grams of pure carbon dioxide gas is reacted with a carbon in a sealed container of volume 3 cubic decimeter. We are happy with 3 because it's already in cubic decimeter, but we must calculate the initial moles. The equilibrium reaches equilibrium, the reaction reaches equilibrium at temperature T according to the following balance equation. Remember, our focus is not on this carbon, which is a pure solid. We don't care about this. By the way, carbon can be in a form of charcoal. Charcoal is a form of carbon. Coal is another form, but for this reaction, I think possibly it could be the charcoal. To produce the carbon monoxide gas, so you can see, we're not concerned about the carbon because it's a pure solid, especially in the calculation of the Kc. We exclude the pure solids and pure liquids. 15,1 is on you. At equilibrium, it is found that the concentration of carbon dioxide at equilibrium, concentration of carbon dioxide is 0,054 moles per cubic decimeter. Calculate the Kc value. So before we calculate the Kc value, we need to know the equilibrium moles so that you can get the equilibrium concentration of carbon monoxide. So where do we start here? We start with the initial moles of this. Or do we even need that? I don't think so, because we already have the equilibrium concentration. So let us calculate rather. We're gonna need that, definitely. Initially, we have put in 60,8 grams, and the molar mass of carbon dioxide, I think we all can agree that it's 44. Or maybe let us show you where this 44 comes from, so that you do not just put it out there. 12 for carbon, 2 times 16, that will give you 44. What is 60,8 divided by 44?
One comma 3818.
3818, is that all?
18 again, sir. So it's
Okay.
1,381818. Check on that. Yeah.
Okay, infinitely and then it carries on. All right. All right, let's keep it at that. It's fine. These are the initial moles of our carbon dioxide gas, 1,3818181818, because it's a recurring decimal. Oh, I see why. Because as a fraction, it has a division by 11, isn't it? It's 152 over 11. Am I correct? No, 110 over 110 or over 55. Yeah, it's over 55. It's something over 55, but there is 11 in a way. That's why it's 181818. Right, that doesn't matter. So we've got our initial moles of this. If you want to, we can also calculate the equilibrium moles of our carbon dioxide by using the formula concentration times with the volume. And the concentration we are told to be 0,054, 0,054 in a chamber of a volume, a reaction chamber of a volume of 3 cubic decimeters, there up there, volume 3 cubic decimeters. What is the answer of this, guys?
0,162.
That's equilibrium. Now with these two, we can calculate now the reacted moles of carbon dioxide. And that is the difference between the two. 1,3818, let me just keep it at that. Subtract 1,62. What is the difference between these two? 1,1 what?
1,2198.
1,298. 1,298. Is that so? 2198.
Yes, sir.
2198
Yes, sir.
moles. Remember that the reacted moles are the ones that we use in your stoichiometric ratio. So without even designing the table, we can look at the produced moles of carbon monoxide by comparing the ratio of carbon dioxide to the ratio of carbon monoxide. We can easily look at this ratio between the two. From the balance equation, 1 mole of carbon dioxide produces 2 moles of carbon monoxide. So for every 1 mole of carbon dioxide, we are going to produce 2 moles of carbon monoxide. But what do we have actually? We've got 1,22 if you want to. 2198. I prefer rounding off. The final answer is 2x. And then when you cross multiply, you've got 1 times x. What is 2 times that? What do we get? 2,4396. Am I correct?
Yes, sir.
Is it 4396?
Yes, sir.
Okay, thank you. Monoxide gas at equilibrium. These are your equilibrium moles because whatever I'm producing is what I'm going to get at equilibrium. This is produced, therefore it is what will be there at equilibrium for carbon monoxide, because when I started the reaction, there was no carbon monoxide. So whatever I'm going to produce from the reaction is what I'll behave in as far as the products are concerned. In this case, carbon monoxide. So these are the equilibrium moles, which I can now use to calculate the equilibrium concentration of carbon monoxide gas using the formula N over V, where N is 2,4396 or 2,44 if you round it off. Divide by the volume of 3. What do we get? 0.8 what? 8132, am I correct?
Yes, sir.
Moles per cubic decimeter. This is the equilibrium concentration of that. And now we can easily write the Kc expression starting with carbon monoxide. We've produced it 2 moles of that. 2 carbon dioxide concentration of that. Equilibrium concentration 0.8132. Equilibrium concentration was 0.054, if you remember quite well. It is given somewhere, 0.054 moles. At equilibrium, the concentration of carbon dioxide is 0.054. So what is the answer there?
Twelve comma 225.
12.25.
12.25? No unit. 12.25, is that what you have said? Okay, so look at what we have done. We didn't use the table in this case, but we could have used the table
Yes,
and
sir.
achieved the same result. We could have used the table and achieved the same result. Looking at carbon dioxide gas producing 2 carbon monoxide gas, because we do not care about the carbon there since it is a pure solid. Look at the initial moles, we look at the change and the equilibrium moles. Initially, we have calculated and found 1.381818. And then we calculated this at equilibrium and we found 0.162. And then initially we had 0. So we look at the difference between this and we said 1x here minus, and we said here, sorry, this will be plus 2x. Minus 1x from the coefficient 1, plus 2x from the coefficient 2. Minus because the reactants are used up. So we see that, oh, this will be 1.381818 minus x will be 0.162. So when we solve for x here, we get, take x this side, 1.381818 minus 0.162. This is where we found 1.29. What was that again? 1.2198. Oh my goodness, what is that? We could have used the table and we are going to find that. And then here we're just going to have this. So that these are your moles that have reacted. And we've got your equilibrium moles. So that we could have easily said, okay, it means that the number of moles of carbon monoxide gas will be 2x, which is 2 into 1.2198. We still could have achieved the same result, 2.4396 moles. That is precisely what we have obtained if you look correctly. So then we can easily use that to calculate the equilibrium moles of carbon monoxide from N over V, 2.4396 divided by the volume of that to obtain 0.8132 moles per cubic decimeter. And you've got the same thing as previously. You have pretty much the same thing. So look at the difference between this. Here, we're still going to do the same thing. We're still going to calculate the initial moles of that. We're still going to calculate the equilibrium moles of that. But from this point henceforth, you could still have used the table method, or you could use this method that we have applied here. Notice that the two methods are equivalent to one another. So you've got your Kc from this point, Kc, carbon monoxide to the power of 2, equilibrium concentration of that. Remember, you're given the equilibrium concentration. This 0.8132 squared and this 0.054. And then when you divide that, you would still get the same thing, 12.25. So notice that the two methods are equivalent. Okay? So notice that the two methods are equivalent. So we could have chosen to say, instead of going the ratio way, we could have just went straight into a table, filled our table up with the correct values, and then went down the normal way that we always have been doing it. So do not think that we are doing things differently. It's the same thing interpreted differently. Any questions? Guys, any questions?
No, sir.
Okay, let's move forward. Question 15.3. In each of the following changes, how will each of the following changes affect the amount of carbon monoxide at equilibrium? At equilibrium. How is this going to affect the amount of carbon monoxide, which is a forward reaction? Carbon monoxide is in the forward direction, so it's the forward reaction. Choose from decrease. More carbon is added. When we increase the amount of the reactants, what happens to the product, Chichi? When we add more product, what would happen to carbon monoxide? Increase, decrease, or stay the same?
Increase.
It definitely will increase. Why? Because when I add more reactants, the reactants will react more frequently to form the product. So this one, it's definitely going to increase. The pressure is increased. Let us look at that. We've got the 2 volumes of the gas, 1 volume of a gas. Increasing the pressure will favor what will happen to carbon monoxide? Sidwell, increase or decrease? Sidwell, are you still there?
Yes, sir.
Yes, what will happen what will happen to carbon monoxide when we increase the pressure?
It will decrease.
Absolutely, because the reverse, we are going to favor the side with fewer gas moles. So this will decrease. And how do we explain that? They are saying, use the Legitimus principle to explain. We are going to tell them exactly what we know about pressure. Question 15.3.2. So let us tell them what we know. An increase in pressure will favor, we are only looking at the gas molecules. The side with fewer gas molecules. Okay, so we tell them that the reverse reaction, according to the balance equation, the reverse reaction has fewer gas moles. Hence, an increase in pressure will favor the reverse reaction. So if we are favoring the reverse reaction, the amount of pressure, the amount of carbon monoxide gas, which is a forward reaction. And that's it. Because we are going to form more of that. I think that is clear by now. And then to end this process, there is this question, which is very interesting, a very interesting question, if you ask me. But we've been discussing that. So let's look at this question. Okay, I think I need to put you here. Yeah. Let's look at this. What are they saying exactly? Okay, the table below shows the percentage mole of carbon dioxide and carbon monoxide in the container at different temperatures. Look at what happens. We increase the temperature. This is your reactant. This is your product. So look at what happens. The amount of your reactants, temperature is increasing. Temperature increases. ST, this is a trend, increases. Look at what happens from 6 to 1 to 0,3 to 0,06. Amount of reactants. Decreases. And look at what your product from 93,77 to 98,68 to 99,6 to 99,94. And the amount of your product, which is carbon monoxide, increases. That tells us something. Because when T increases, the products are increasing. Is this reaction exothermic or endothermic? Chichi, what do you think?
Endothermic, sir.
It's definitely endothermic. Forward reaction is endothermic because as the temperature increases, the forward reaction is favored. So it's endothermic without a doubt. Refer to the data in the table to explain your answer. So we can easily tell them that the very same reasoning that we have observed it, that ST temperature increases, the amount of products, that is the carbon monoxide gas, increases. So what is that telling us? It tells us that this means that the forward reaction is the one that is favored. That is what it means. So that is why we are saying that this is endothermic, because the forward reaction is favored by the increase in temperature. So we can then conclude, therefore, forward reaction is endothermic, because when we increase the temperature and the forward reaction is favored, the forward reaction is endothermic. Simple as that. Use the information to determine the temperature. Use the information in the table to determine the temperature T. Clearly show how you arrived at the answer. Okay. So how are you going to do that, guys? We are going to calculate the percentage yield of carbon monoxide. Let me repeat this. The way to answer this question is to calculate the percentage yield of carbon monoxide and compare it against these values. Then we are going to then look at the percentage yield against the temperature. So how do we calculate that? We are going to say the percentage yield of carbon monoxide would be equals to the number of moles of carbon monoxide at equilibrium divided by the total number of moles. Times 100. So what are the moles of carbon monoxide at equilibrium? I think we have them this side. We have 2,4396. Divided by the total number of moles, 2,4396, plus the moles of your carbon dioxide. What is the equilibrium moles? 0,162 at equilibrium. So this was a tricky question, but not really that tricky. 1,62 times 100. What do we get when we do this? What do we get, guys, when you do this simple calculation?
93,77.
Then we go and compare 93,77%. Ah, there you have it. The temperature is 827 degrees Celsius. Therefore, T is 827 degrees Celsius. Simple as that. Simple as that. Again, it was a question of understanding percentages. This was a very cleverly phrased question. They were trying to trigger you. They were trying to be smart with you. So you had to outsmart them by saying that what is on the table is actually the percentage yield of carbon monoxide. How do I calculate the percentage yield? I'm looking at the amount, excuse me, sorry, the amount of carbon monoxide against the total number of gas moles in the container. And that is what we have done. So we looked at the number of the moles of carbon monoxide at equilibrium against the total number of moles at equilibrium. That gives us the percentage yield of carbon monoxide, 93,77. Wow, that was a beautiful question. That was a very beautiful question. I hope you guys understood as we're about to wrap this up. Any questions before we move on to question 16? Sidwell?
No questions, sir.
So can I please see 15.2.2?
15.2.2. Okay, let's go there. Oh, we have skipped that one. How did we miss it? I don't know how we missed that question, but let us do it. Minimum mass of these that must be present in a container to establish this. We use the ratios again. We know we have to use the part that speaks about what has reacted, 15,2,2. Not sure if I'm going to be able to squeeze this here, but let us try to squeeze it. So what are we looking at? We're looking at the reacted moles of carbon against the reacted moles of carbon dioxide gas. We are looking at the reacted moles. By reacted moles, we need to start with the theoretical ratio. Theoretical ratio from the balanced equation. So we start there, stoichiometry there. So we said one of these requires one of that. That is what the balance equation says. So we look at this balance, 1:1. Thanks for reminding us, Chichi. I have completely overlooked that. 1:1. And what is the reacted moles? We need to look at the reacted moles of this. We do not know this, but we do know how many moles of that have reacted of carbon dioxide. We have said reacted moles 1,2198. 1,2198. Then we can calculate X. 1,2198 moles of carbon that is required. So what is a mass now? Mass will be this multiplied by the molar mass. 1,2198 multiplied by 12. That is a minimum mass. What is that? Correct to 2 decimal places.
14,64.
That's it. And that was that. Thanks, Shichi. I don't know how I missed that question. Completely missed it. Oh, yeah. So that is about that, guys. That is basically about this question 15. Before we move on to question 16, any questions, Sidwell? Or any comments, rather?
No, sir.
Look at the last question, 16. So, guys, next week we are introducing work, energy, and power. So I think we'll work from Monday through to Thursday. Monday through to Thursday, that is, so that we can make up for the time lost this week. We are falling behind schedule and we need to hurry up because examination starts in about, is it 3 weeks from now? Yeah, but very pretty soon. The dissociation of iodine molecules to iodine atoms is a reversible reaction taking place in a sealed container at 727 degrees Celsius. The Barnes equation for that is that. So one of these decomposed to produce 2 atoms of iodine. One molecule of that is broken down to 2 atoms of iodine gas, and it's a reversible process. The Kc is 3,76 times 10 to the power. Write down the meaning of the term reversible reaction. That one is on your radio definitions. Actually, the pressure of a system is increased by decreasing of the volume. The pressure is increased by decreasing the volume at a constant temperature. How will each of them be affected? Kc constant. Can pressure affect the Kc constant?
No.
It cannot. What affects the Kc value?
Temperature.
Only temperature. So what is the answer here?
Remains the same.
Remains the same. Now we have increased the pressure. What will happen to the number of iodine gas molecules? Increase, decrease, or remain the same?
Increase.
Definitely, this will increase. And how can we explain that? We first give them the fact, and the fact is an increase in pressure will do what? Which side will be favored? Will favor the side with?
Yes, number of moles.
Absolutely. Will favor the side with the fewer gas moles. Let us be specific that it's gas moles. And then we look at that and we tell them that, okay, the reverse reaction is that side, which has the reverse reaction has fewer gas molecules. Hence, it is favored. Hence, the reverse reaction is favored and the amount of that increases 16,4. Now we lower the Kc value. Look at what they're saying. From 727 to 227. What happens to the Kc value? It drops drastically. Temperature decreases, Kc also decreases. When the temperature is decreased from 727 to 227 degrees Celsius, the Kc value drops. Why do we say it drops? Because look at the exponent. It becomes more negative, power of -12. That is a smaller value than the initial Kc value. So in that case, we can easily tell them that the forward reaction is endothermic. How do we know that? Forward reaction is definitely going to be endothermic. Fully explain your answer. So how to explain our answer there? We start by telling them that Kc, okay, sorry, for an endothermic reaction, decreasing the temperature will favor the reverse reaction. For an endothermic reaction, decreasing the temperature favor the reverse reaction. So what happens after that? Then the amount or the concentration of your product will decrease, and the amount or the concentrations, by the way, of reactants will increase, will increase. So what happens? Since Kc is proportional to the concentration of the product against the concentration of the reactants. So this is a proportionality. So what does this tell me? If this one goes down and this one goes up, this one will definitely go down. In a fraction, when the numerator goes down and the denominator gets bigger, the value of the fraction gets smaller, which in this case, the fraction represents the Kc. So if the numerator gets smaller and the denominator gets bigger, the value of the fraction gets even smaller. That is what happens. That is what a fraction is about. The numerator decreases and the denominator decreases. So that is the case. Since Kc is proportional to this fraction, and then it means that therefore Kc decreases with the decrease in temperature. That is how we have arrived to this conclusion. So we need to first understand that for an endothermic reaction, decrease the temperature will favor the reverse reaction. So the amount of product will decrease and the amount of reactants will increase. Since Kc are proportional to that, the decrease, Kc will decrease with the decrease in temperature only for the endothermic reaction. Questions? Right, let's look at this. A certain mass of iodine gas is sealed in a 12.3 cubic decimeter flask at 727 degrees Celsius. Kc is equal to 3.76 times 10 to the power of negative 3. When equilibrium is reached, the concentration of iodine atom is found to be at equilibrium. Concentration of iodine atoms is found to be that. Calculate the initial mass. So what are we having there? Okay, I think I see. Right, let's start with this question 16.5 now, which is the last question for this. So we're gonna first calculate the moles of iodine gas, of iodine atoms, sorry. Concentration times the volume. And we are given the concentration to be 4.79 times 10 to the power of negative 3. And we are given the volume to be 12.3 cubic decimeters. Can you please kindly assist with your calculators? What's the answer there? Hello, what's the answer?
5.84 times 10 to the power of
Zero
negative 11.
Okay. What's your answer, Sidwell, first? 5.84
times 10 to the power of negative 11.
No ways. 4.79 times 10 to the power of negative 3 times 12.3. No ways.
Oh,
So it's 0.0589.
0.0589.
Yes, sir.
Are you sure?
17 at the end.
Or 17. Okay, so that is the answer there for the moles of iodine atoms. And then we can use this to calculate. Did we need this? I don't know, but let's just calculate the Kc value. We'll use the Kc value, iodine atoms, there are 2 of those, and iodine gas, there is 1 of that. Remember, we are given the Kc value to be 3.76 times 10 to the power of negative 3. We are given the equilibrium concentration of that to be 4.79 times 10 to the power of negative 3. This must be squared, divided by the equilibrium concentration of the iodine gas. Then we can cross multiply, which means this comes here, squared, divided by. What is the answer there, guys?
Six 6.05 times 10 to the power of negative 3.
This is the equilibrium concentration. Now we can use this to calculate the number of moles of the iodine atoms at equilibrium, because this is the equilibrium concentration using the formula concentration times volume. So it's 6.05. Yes.
That answer, the previous answer, sorry, I made a mistake. It's 6.1 times 10 to the power of negative 3. Or 6.102.
6.1
02
102.
times 10 to the power of negative 3.
Okay. And the volume, remember, is still 12.3. When we multiply these two, what do we get?
0.075.
75 what?
Must I
I
continue?
need more. Say again.
Must I continue?
Yes, I need more. We'll round off only the final answer, guys. We round off only the final answer. So I need more. 0 only.
5
Uh-huh.
0564973 4.
05649.
734.
Mhm. Let's make a habit of only rounding off the final answer, because the more you round off, the further away you drift from the correct answer. And there is a certain range of answers that they accept. So if your answer is too far from the acceptable range, you're going to get the final answer is wrong because of multiple rounding off. Only round off the final answer. In between, highlight everything that appears on the screen. Write the whole thing as it appears on your calculator screen until you reach the final answer. I hope that is clear, because I won't be repeating this all over and over again. These are the equilibrium moles of this. So what can we do now? We can go to our table if we want to. We can now go to our table and say, we want to look at this reaction. Look at the initial, the change, and the equilibrium moles. Initial moles, we do not know. Equilibrium moles, we have them as 0,075. Okay, due to the limitation by the space, I'm only going to write that. And then there, the equilibrium moles were 0,058917. 0,058. And then remember that this change column here, we've got minus 1x. Here we've got plus 2x. We had nothing there. We don't know what was there. But we know that this is equals to 2x. We know that this is equals to 2x. So we have 2x being equals to 0,058917. Then we divide both sides by 2. What do we get there? 0,02294. What is this? 4585. Is that correct?
Yes, sir.
So we've got our x there. And then if we can call this initial moles as A, then we're going to have this to be equals to A minus X. So your A minus X will be equals to 0,0. What was that answer? 70505. Was this a 6 or a 0? And then we've got our X. We got the X as that. A minus 0,0294585 equals to that. And then we take this side, it becomes a positive. So we've got the initial moles of that being the sum of 0,07050504974 plus 0,02945. Okay, I don't know what is going on. 585. What is the answer, guys? When you add this for me, please. You can round it to at least 4 decimal places now because we are closer to the answer. What is the answer when you add these two?
0,099. 0,0999.
999. So it's
6.
approximately 0,1. Eh?
Yeah.
Yeah, it's 0,10 moles. These will A represent the initial moles. So what do they want here? They want the initial mass. 0.10. So we go there. In the periodic table, we found, I think it's 237. I'm not sure, but let's just find out. How do I get the periodic table here? That's paper 1, man. It's paper 2. Okay, let's check. I think it's about 237 from the periodic table for iodine. Molar mass of iodine gas from periodic table. It's in group 7, 127. 127. And what do we get?
25.4.
25.4 grams. That's it. You are done. So that is how you'd go about doing that. So it's all about correctly interpreting the balance equation and correctly using the given values, not forgetting where which number fits. Because the most important thing is to correctly fill this table. Then we'll never go wrong. You'll never go wrong. So we didn't know the initial moles of iodine gas. We were not told. So we gave them any number A. You can use any symbol because we do not know that. But we know the change here. It will be 1 mole of that decomposes to produce 2 atoms of the iodine gas. So at the end, the equilibrium is A minus X. This side equilibrium have got 2X. So when we use that, we solve for X. We can easily find the value of A like we've done. And then from the number of moles, these are the initial moles. A represent the initial moles of the iodine gas. From there, we're able to easily calculate the initial mass of the iodine gas. Any questions? That's it about question 16. Any questions? Because this is what we had in store for you. Any questions, guys? I hope you guys are seeing what is going on here. So I've given you an opportunity to work through 16 different question sets. Completely different. One question was completely different from the next. So we had an opportunity to work on 16 different sets of questions on under chemical equilibrium. So I hope you guys have noted this. So I'm gonna trust, I've given you the tools. Now it's your job to go and get as many questions as you possibly can and try to solve them, but make reference to what we have already discussed. Make reference to what we have already discussed. Go through the very same questions, 16 questions. Make sure you can answer every single one of them. Wherever there are problems, you may text me, you may call me, but preferably text because I could be in another session. So preferably you can text me, then you can discuss. Next week, Monday, 9:30, work, energy, and power. We are starting with that. Next week, Monday, 9:30, work, energy, and power. We are introducing that. So let us meet then. Until then, keep well, enjoy your weekend. And yeah, that's it. Unless if there are any questions, because from my side, that's all I had in store for you. Okay, then if there are no questions, cheers guys, bye. I'm out.